Quick overview of this section. We're going to talk about generating signals. We're going to talk about analog modulation and then digital modulation. So let's get right into it. So what is a signal generator? Well, it generates signals. There's a lot of ways to do that, but before you get to that, first you need to understand what a signal is. So we've got two different views of signals up here. We've got time domain, we've got frequency domain. Now, we're going to talk mostly about periodic signals today. We like periodic signals because, thanks to Fourier, we can transform them from time domain to frequency domain. You can do that with non-periodic signals too, but there's a lot of limits. We often cheat. We just pretend that a signal is periodic. We're also going to establish a little bit of vocabulary here. RF signals generally talk about less than 6 gigahertz. Between RF and at 6 and 20 to 70, we usually call those microwave signals. Above that, we've got millimeter wave. These definitions aren't exactly solid, but those are kind of the guidelines we're going to use today. Kind of a general idea of how we generate RF microwave signals. You always have some sort of reference oscillator. That's the core of your system. It's kind of what establishes the base. You can never do better performance than your reference oscillator. We're going to take that reference oscillator, we're going to multiply it, we're going to divide it, we're going to do all sorts of things to it, and that's going to get us whatever frequency we want out of it. And we do that in the synthesizer section. Finally, you have to amplify, you have to attenuate, you have to do whatever you need to get the right amplitude out of this. And so that takes place in your output section. The synthesizer is probably the most important section, most interesting, and kind of the core of that is the VCO. So we could talk about a little bit about the VCO. VCOs, you have some sort of tuning gain. You put a DC voltage in, you get a frequency out. But that tuning voltage, it's not really a linear response. It's got kind of this curve to it. So how do you linearize a nonlinear system? You wrap that in a feedback loop. So in this case, our feedback loop, we call that a phase lock loop. We've got our VCO in there. We take the output, we combine it with the reference signal through this phase detector. If they aren't locked perfectly together, we get some sort of air voltage, and that adjusts the tuning voltage, and that adjusts our frequency output. And that cycle loops back, feeds back on itself until we've stabilized, until we get the exact frequency that we need out of it. We've got one other thing in here, the loop amp and the filter I just want to mention. Later on, this is going to show up in one of our slides. So this phase lock loop, it's not perfect. You have to be somewhere in the vicinity for it to loop. Otherwise, it's going to go crazy and you might get nothing out. You might get a crazy oscillation out or something. But that loop filter kind of determines where that gain trails off. So we're generating a signal. You need to know what can go wrong with that signal. So nothing's ever perfect. We have all these things that can be measured, that can be quantized. Your frequency, you've got a finite bandwidth, you've got a finite range that you can generate in. You've got a finite resolution that you can tune to. You can't go to any arbitrary frequency always. How accurate that is, that kind of comes back to our reference oscillator switching speed. You got a lot of the same things with amplitude. And then finally, you got spectral purity. Spectral purity, you can kind of broadly categorize this into two sources. Noise, we've got broadband noise and phase noise, or spurs. So spurs can show up. There's a lot of ways to get there. Generally, we're kind of hiding some things right now. There's going to be going through some mixer stages, some amplifier stages. All those can generate harmonic products, non-harmonic products. And you get these spurs out here. I like this slide because it kind of breaks them down a little more. Subharmonics, non-harmonics, and harmonics. And those all come from different sources. They come in different amounts, but they can all be problems. Whether you care about these things or not depends a lot on what you're trying to do. But they're all there, and you need to be aware of them. If you don't know it's there, you don't know if it's a problem. So why do you care about spurs? When do you care about spurs? Well, your spur can mask a signal that you're trying to measure. If you're trying to measure a harmonic that your device is creating, you don't want your source to be creating that harmonic as well, or you're going to mask it, or you can mask it. You care about noise, you care about everything, because those can all mask smaller signals. We showed phase noise and thermal noise on the previous slide. On this second and third row, if you have these very small received signals, those can be hidden under your thermal noise. If they're very close to your frequency of interest, or to your generated frequency, they can be hidden by the phase noise. So all these things tend to matter. Again, with phase noise, so kind of the classic case for phase noise is this instantaneous deviation of your expected signal. When you're dealing with radar, you get a very small frequency shift if your target is moving. And that frequency shift, it's going to be pretty close to what you generated. It's going to be very low down in power. And so it can be easily hidden by phase noise. You need a very high quality source with very, very low phase noise to be able to measure that signal. Or it's just going to be totally hidden under that, not able to be picked up at all. Phase noise, we view phase noise on this phase noise chart. We have phase noise measurement systems. It's a big deal. But you have this classic phase noise response as you move in offset frequency on the x-axis from your carrier frequency. So 0 hertz would be exactly on your frequency. Then we're talking 1, 10, 100, 10K, 100K offset. But you get this response. Close in, you have the loop bandwidth of your phase lock loop in it. It's able to lock your VCO, which has poorer performance than your reference oscillator, into the phase noise of the reference oscillator. Eventually, as you move farther and farther out in bandwidth of that phase lock loop, you get this table that evens out until you hit the performance of just your VCO. Now you're outside the phase noise performance of your reference oscillator. That goes down again, and then you hit the thermal noise. You can't really get around thermal noise. It's always there. It's a property of physics. And this is the classic response. What can you do with a signal generator? I think when you're just generating single tones, well, you can use it in a lot of places. In a classic receiver, which you'll see this diagram a lot more when we talk about signal analyzers, or we already did talk about signal analyzers, what I'm saying. You probably saw this diagram a lot. Well, if you replace the internal sources with the high quality external sources, you can often get a lot of benefit to the performance here. So this little chart down here is showing the internal source in blue, and we've got all sorts of noise in here. And then we've got, if we replace those with a high quality external source, we can get a much better idea of what our signal actually looks like. Another test you can do when all you're doing is generating CW tones, well, you can combine this with the power sensor, and you can start to measure amplifier characteristics. You need to know the compression ratio or the compression point of your amp. You can do that with just a signal generator and a power sensor and a little bit of logic in there. So that's the basics of CW generation. I'm going to move in and start talking about analog modulation here. Analog modulation comes in a few flavors. This is really your master equation, though. You've got amplitude in here, you've got frequency in here, you've got phase in here, and it's all wrapped in a sinusoid. So this is coming all down to what are you doing to a single tone. There's a few ways to do this. You're always taking some sort of baseband signal, which is your low frequency signal of interest. You're combining it with a higher frequency signal, and you're modulating that high frequency carrier somehow. Amplitude, frequency, and phase modulation. With frequency and phase modulation, you'll note that the charts look very similar. They're very closely related. In both cases, we're modifying the argument to that sinusoid. The argument to the sinusoid is actually a phase value. So when we do frequency modulation, if you look at the instantaneous, it's still a phase that's being modulated. They're related by just a derivative, so they're very similar. Amplitude modulation, there's a few key metrics here. You've got your modulation frequency, that's your carrier. You got your depth of modulation, so if I have my baseband signal go to its absolute negative value, how deep have I brought down my carrier? You've got key measurements that you want to do. You can always measure the distortion of your modulation. Once I've modulated and demodulated, how accurate is my signal? Did I get back to my original signal, or is there that plus some stuff? AM radio, everybody knows AM radio. Really popular early use of modulation. I think that AM radio was popular mostly because the receivers were so cheap and easy to build. You can build an AM radio with a filter and a diode. So it's not that it's a superior modulation scheme or anything, it's that it was cheap to build. We're going to come back to that later. Frequency modulation. So you have a lot of the same kind of characteristics here. Modulation index, modulation frequency. You've got a lot of things you can measure. What I want to point out here is that frequency and phase, again, very similar. Phase deviation, modulation rate. So both cases, I'm going to flip back and forth here a little bit, but if we look at the equation at the top, we see kind of a similar effect happening here with this argument to the cosine. So they both very similar modulation schemes. Moving to pulse modulation, this is the last analog modulation we're going to talk about. Popular type of modulation, but you're just turning your signal on and off. If you remember the Fourier transform of a pulse, you get a sync signal, the sine x on x. And so when you do pulse modulation, you get your carrier and you get this sync response. And there's a lot of ways to measure this, but you can get back to all your time domain characteristics by looking at the frequency domain, the spacing of the tones and the spacing of the nulls. So it's an interesting modulation for thinking about the Fourier transform. So now that we have all those analog modulations, how do we modify our source to get back to perform those modulations? Well, remember our synthesizer section gave us control over frequency and phase. So we can take our FM source and we can run it right into that section. We can control frequency and phase. We've got our AM source. Well, we had an output section that controlled our amplitude, so we can route that into our level control, our automatic level control, ALC. And we've got amplitude modulation. Now the pulse source, it's tempting to think of that as an amplitude modulation. You're doing on-off with your amplitude. But we actually run that to a whole separate section, the pulse modulator. That's because we can get a higher on-off ratio by turning it off on the other side of the amplifier than you can with the AM source. If you turned it off with the AM source, you'd still have the noise of that amplifier and everything going through there. So you wouldn't get as high of an on-off ratio, which is one of the important characteristics we need to measure. So now that we've got modulation, how do we modify our test setup and do a measurement? So we want to measure our distortion. Now we need a more advanced receiver. Before we just had a power sensor. Now we have an actual receiver. We have a spectrum analyzer. That's able to do the demodulation, and then we can look at our original signal and we can measure the distortion. What was there that wasn't before? You do need to know what the spec of your source is. You need to know if you're measuring the source or if you're measuring your device. And so there's this little equation up there that's giving us receiver distortion, and you need some margin. That's going to depend person to person, but a lot of times 10 dB is a good number to start with. So you need your source to be 10 dB better than your device. I'm going to move into digital modulation. Now this is really the way forward. Almost everything we do is digital modulation. We've got some demos set up in the back that are showing digital modulation. We spend a lot of our time on this. There's a few basic categories: amplitude shift keying, ASK frequency shift keying, phase shift keying, and then we can do both. Now, amplitude, frequency, phase, those were all the analog characteristics, right? Well, if we take those same things and we move them into discrete levels, now it's a digital modulation. We can also combine these. Amplitude and phase, those are orthogonal. They aren't really linked together, so you can do them both at the same time. And that gets us to this Quadrature amplitude modulation. That's really what most digital modulations we see today are. So when we look at the quadrature amplitude modulation, we see a few different representations, but this constellation diagram is one of the common ones. So I like to think of this. I was in school, I was forced to do a lot of phasor diagrams. I don't know if anybody else was, but I think of this as a polar coordinate plot. We've got all these points here, and they each are a combination of a specific magnitude and phase. We're going to look more at that in a minute. Now we can also combine other modulations. We've got this FM chirp down here. We've combined a pulse modulation with an FM linear FM response. So this is almost more of a combination of digital and analog. So it goes back to what I was just saying with the constellation diagram. We've got an independent magnitude and phase, and we can place our signal at any point on that. If we have control over phase and magnitude, we can place our point at any place on that constellation diagram, right? Now this assumes that we have a constant frequency. If our frequency isn't correct, if it's not locked to what we expect, we're going to see that point just travel around in a circle. So that's one thing that you need to get right. So with polar diagram, we've got magnitude and phase, but we can break that into orthogonal linear vectors, I and Q. But we've got to think here, what's a 90-degree phase difference for those vectors? Well, sine and cosine are 90 degrees apart. So when we talk about I and Q in phase and quadrature, we're really talking about sine and cosine. Before we get there, let's talk a little bit about why you want more than 2 points, why you need to do this. So really what we're trying to do is transfer binary data across, right? Binary data 0 or 1. For a given data rate that we want to transfer, we're going to have some necessary bandwidth. And that is given here 2 over t. T is the period, the clock period. Now, if we start grouping those up and we have more than 2 points, all of a sudden our main lobe is 2 over s. S is the sample rate, or the symbol rate, sorry. So if we group up blocks of bits into 2, now we've just cut our bandwidth, required bandwidth, in half. If we group it into 4, we've just cut it down by a factor of 4. So we can group these blocks of binary data up. We can combine them into one symbol, one discrete point on that constellation, and we can transfer that to limit our bandwidth. Now you do need more points on the constellation diagram, means you need more noise immunity, more suppression of distortion, all these things that distort how that constellation diagram is going to be presented become more of a problem if you have more points on that. If we group together our bits into blocks of 2, we need 4 points to represent all the combinations. That's a QPSK, quadrature phase shift keyed. If we group up into blocks of 4 bits, we need 16 points, 2 to the 4, 16. And that gets us to our 16 QAM quadrature amplitude modulation scheme. Now, for a given symbol rate, a given resulting bit rate, our bandwidth has shrunk down quite a bit once we move to that higher modulation scheme. In the back here, we've got, I think it's a 256 QAM signal, so you can really cram a lot of bits into one symbol. Again, what goes wrong with IQ modulation schemes? Well, what do you need to measure? You need to measure the bandwidth, you need to measure the frequency response, the IQ gain balance. So all these things that can go wrong are going to distort where that point is from where it should be. So how do we get there? Why are we even talking about this? Well, it turns out that this scheme is pretty easy to make. I was talking earlier about sine and cosine. So if we start with a single oscillator, or single carrier, and we phase shift it by 90 degrees, pi over 2, we have a sine and we have a cosine. We can take our amplitude levels, our I and Q data, as raw bit streams, straight out of a digital analog converter, and we can combine those with the carrier. And now we've got our two separate carriers modulated by the amplitude. If we sum those together, we get our single point on this constellation. So if we go back to our overall block diagram, how do we modify this? Well, right in between the synthesizer and the output, we jam in all this stuff. We've got two mixers, we've got our 90-degree phase shift, and then we've got a couple of digital analog converters. So it's a pretty simple, pretty cheap scheme to do in today's modern age. Digital analog converters, very common. Mixers you always have in these systems anyway. You might be saying to yourself, well, we had phase and amplitude control before, why didn't we just reuse those systems? Well, it turns out you can do things much faster with this sort of system than you could before. If you're trying to adjust the phase of your synthesizer, that's going to take some settling time. It's going to take more time to work out. You just can't get the same symbol rate that you can with this sort of system. Again, there's some stuff that has to happen for this to all work out. You got to load all your binary data into the pattern RAM. You've got to map it to the symbols. So you've got to do that grouping and mapping. You need to do some sort of pulse shaping to your pulses. So there's an output filter. It could be digital, it could be analog. And then you've got to convert it out to your analog before you can mix it. We have sources like this one here that are modular. If we look at these four modules that comprise one source, we have a vector modulator, we have a source output section, we have a synthesizer and a reference. These are all the blocks that we've been looking at. So this isn't a theoretical thing. These are real kind of chunks. Again, now that we have a digitally modulated section, what can we do with it? Well, we have some bit stream that we know what it is. We run that through all this modulation. We go out to our DUT, it demodulates, and it comes back to some bit stream. So if we know what we have and we know what we started with, we can compare those and get a direct look at the error rate, the bit error rate. Most digital systems going to have some sort of bit error rate spec, and we can measure this and test to see if you're meeting that spec. How many errors are tolerable? Another thing that we test a lot, how tolerable is your receiver to an out-of-band interference signal? So if we have two sources, we can send our modulated signal out. We can combine it with another signal generator that's generating a strong tone nearby. And we run that all into your device, and we see if your device can still demodulate it. This is a common test if you're working in a band that's nearby some other non-public band that you can't control. If you're working in the presence of other band, like when you're working with Bluetooth and you're in this ISM band, there's a whole lot of other stuff that's going on. So how well can your device tolerate all those unwanted signals? Common measurement here, we're talking about adjacent channel power. Once we run a modulated signal, there's a lot of tones going on at once. We run it through your device. You get a lot of intermod distortion. It starts filling up the channel nearby. So if you are in one of these schemes where there's a lot of separate channels and they're all right next to each other, if your device is throwing a lot of power into that adjacent channel, it's going to interfere with that channel's ability to function. So you need to be able to run the modulated signal. You can't just test your device in CW, even if it's something like an amp. And finally, probably the thing we spend the most time measuring, EVM, air vector magnitude. We have all these discrete points on this diagram that we're trying to get to. Air vector magnitude kind of sums up all the separate things that can go wrong, and it gives you one number that tells you how close am I to where I should be. There's a lot of things that can go wrong. On this chart, we see that the corners here are moved in just a little bit from where they should be. So these corners, think about your magnitude and phase vector. Those are the largest magnitude on this entire graph. So that's probably an effect of compression going through some part of your signal chain. We see a lot of just kind of spreading here, and that can be random noise. That can be phase noise, though. That could be thermal noise. You've got to look further in to find out what's wrong. Air vector magnitude is a really handy number. If it's low, you just know it's good. But if it's high, you have to look a little further to find out what's wrong. Sometimes you'll see kind of a spreading. You'll see this spreading along this curve, and that can tell you that your clock is not quite right. It's maybe a little bit off from what frequency it should be. So there's a lot that can go wrong here. Sometimes you just see one axis is off a little bit more from the other, so you get a skew in there. Tilts the whole thing. Yeah, how do you correct it? Well, it depends a lot on what's wrong. Some of these things are kind of expected to go wrong. Things like the channel flatness, it's normal and oftentimes expected to have some ripple in across your bandwidth, and you can correct that at least partially with EQ to bring it back to a flat channel. Other things, if it's a skew and it's constant, you might be able to correct for that as well after the fact. But if it's a random variation, if it's jumping all around, jittering a lot, those things you can't always correct for. You have to go back and improve the actual clock source or the oscillator or whatever is causing that problem. So it's highly dependent on what's wrong. Okay, so I think I got through that a little fast maybe, but kind of wrapping up. Are there any questions here? Huge variety of sources. Some of these analog sources designed for very low phase noise. Some of them are vector modulation sources designed to give you wide bandwidth. Some of them are designed to do a little bit of everything. Got a huge variety of sources here. We've got a few in the back. Come talk to us about them. See what you think. Just some resources up here. You can go find a lot more resources on our website. And I think I'm going to let you go for a break early. So.